can you predict like this gene expression or gene co-expression from cell perturbation? Basically, can you model a cell well enough that if I say I'm going to give it this compound, then can you predict how which genes turn on and off, or which proteins are expressed? That is, a big challenge, is that if we can model that, then we can sort of do computational screening of compounds.
Hi, everyone. Welcome to episode 16 of the Pollock Principle. And I'm here with Andrew White. I'm actually very, very excited to have this conversation. I've been trying to get you on the podcast since the very beginning, probably. I'm pretty sure I sent you an email maybe 3-4 months ago, and then finally the schedules aligned, and I think it's going to be, a lot of fun. So let me, maybe, I don't want to do a long introduction, but just to let everybody know, right? I think maybe you are the first scientist that tried to use language models for chemistry, or if not the first, definitely one of the first on record. And I think that's how we connected in Seattle back in the day, like a couple of years ago. So maybe to get everybody kind of up to speed, I'd love to hear a little bit from you. Basically how you got into chemistry, how you start using AI and language models for chemistry, and kind of what led you to this, first at Register, right? And then now at Future House.
Yeah, awesome. Yeah, I think I'll start with a little anecdote, okay? Because, you brought up ChemCrow. So ChemCrow is this paper that came out in, I think it was late March or early April in 2023. And this was the first paper on using large language models with tools to do chemistry. And this paper was like, I was in an airport, actually in Seattle, and I got a phone call from Gabe Gomez, who's a professor at Carnegie Mellon. And he was working on a paper as well on this topic. And we actually our papers ended up coming out on the same day. But Gabe called me and he said, he was working on a paper on using language models to do chemistry tasks. And he said he's really worried that someone's going to scoop him, but he didn't have like high enough rate limits from OpenAI to complete the project. And I said, okay, Gabe, that's fine. You can, I gave him my OpenAI key and said, you can use my key to finish the project. And by the way, I think the person scooping you is me. And he was like, oh my God, okay. And so he ended up using my API key. I think it ended up spending $1,000. And then we held our papers and we agreed to put them out on the exact same day on arXiv. So, I think we'll say that we were simultaneous on our papers, and his was called Co-Scientist. Later on, we were on a panel and he heard that my paper was called ChemCrow, and he was like, wow, we haven't named our paper. We're going to go back and come up with a name. So they called it Co-Scientist. But then unfortunately for him, Google launched a product called Co-Scientist this year, and Gabe, his paper now is a big semantic overload with Google's product on a Co-Scientist. But anyway, there's a little bit of history of ChemCrow. There's many twists and turns in getting that paper out, because it came out around the same time when people were very concerned about the progress of language models and things like existential risk. And our paper was the perfect punching bag to be like, look, here's an example of how these things could run away. Anyway, but yes, do you want me to? I'll give a little bit about me, how to got chemistry and stuff.
Oh. Yeah, I mean, there's lots of things, and I have a list of questions, and then I got even more, from listening to you. So, but let's do a brief intro. Like, how do you even get into chemistry at all?
Yes. So when I was I did a PhD in chemical engineering, and I did chemical engineering because I basically wanted to do chemistry and programming and physics and engineering, and luckily there's something called chemical engineering which puts them all together. And so that was sort of, what I wanted to do. And then when I did a PhD, I went to a group and said, I want to work on computational modeling of chemical systems, but I want to do it connected with experiments, because, I just did a lot of icing models work and pop models. And these are, really physics problems that have a very loose connection to chemistry. So I really wanted to get in a real lab doing experiments. So I worked in a experimental lab. And then I did this for a long time. Basically, I did my postdoc in a lab that was trying to work on putting experiments and simulations together. And then, in 2019, I finally started looking into machine learning more seriously. Actually, at UCLA, at something called the Institute for Pure and Applied Mathematics, which had a 3-month program where they help train people to learn machine learning and applied math who were from a domain that's not there, from a other domain. And so started taking it more seriously. And I was really excited about the topic because it was very much connected to experimental data. And so I kind of got in there, and then wrote a few papers, and that led OpenAI to reaching out to do red teaming for GPT-4. And that led me into the LLM space, more to the frontier part of it. And then that led to ChemCrow, and ChemCrow led to Future House, which I co-founded with Sam Rodriguez, which is like a nonprofit research institute focusing on building AI agents in the domains of science, like biology and chemistry. Anyway, so that's like a world introduction. So
There's so many interesting things, right? But you're like, why crows? I never actually got it. It's just because they're smart. So I have in my backyard, but like sometimes I have crows that come over and they bother me. They walk like they own the place, and so I sometimes go and I have to scare them away, right? And I was like, why would you name it Camp?
yeah, so actually, okay, good question. So when we wrote the ChemCrow paper, like I had been doing red teaming. And so like I was trying to take GPT-4 and make it do dangerous chemistry. And it just could not keep track of atoms or keep track of chemical bonds. It really couldn't do anything. And so, but then I had this idea of this React paper came out, and this paper called Miracle. And these are like papers about connecting LLMs to tools. So I tried it in chemistry, and all of a sudden it started working by like moving the burden of counting atoms and knowing how to make a molecule, and moving that to a tool, and then having the LLM sort of drive the user to the tools. So that was kind of a breakthrough that made it possible to do any kind of chemistry with LLMs. And at the time, there was a paper that had come out that was called, Are Language Models Stochastic Parrots? And it was this idea that language models like maybe are just parroting their training data or just doing interpolation. And I thought, okay, like that's what I felt like at first. But then once we put it with tools, it was doing very well. And so crows actually can like parrot English or spoken language like parrots, but then they know how to use tools. And so we thought that, ChemCrow is like taking the language model, which is like the speaking part of the bird, with the tool use, and you put them together and you get a crow. So that was the idea of the crow.
It's interesting. I definitely have seen videos of people teaching crows to do nice stuff, like picking money over the street or something like that, right? It's like, okay, that's a
Nice. I don't know. Yeah, I guess so.
for the owner for the trainer of the crows, it definitely is, right? Yeah, no, but that's that's an interesting thing where like and I think it was a few months ago that GPT, I guess 4.5 can run RDKit, right? Which means I guess like it can run basically the same things that humans can, right? So like counting atoms, for example, is not that complicated anymore, right? Like it doesn't have to go and read the formula. It can just write the one line of code, and then yep, that's it. Which I always thought it was very, sometimes people go and say, well, LLMs are limited in one way or another, right? Because they can do very complex things in one shot, right? Like, people have been, posting images of ChatGPT trying to generate a map, on LinkedIn, right? And it can't do it, right? And then, asking it to count atoms, right? In a formula, right? And of course, they don't necessarily have that capability, right? But like even, humans, right? I don't think there's a lot of people that can draw a map of Europe with every single country and every single border from the top of their head, right? Without, kind of like having to actually go and check it, right? So it always seemed unreasonable to me to expect the language model to be able to do that, with a one-shot kind of prompting without using tools. So the trick, was always like, well, how do we let those models, run tools, right? So I don't understand why there's not more focus on, well, let's just make sure that they have all the tools that humans, would need in order to do that, right? And that, hopefully they work. And I know in my impression, they can do things, just as humans can, in many domains, right? The moment that you put the tools in front of them.
Yeah, I think that's true. One test you can always do is you can go to these language models and you can ask them like, hey, how do I, make the pKa go up on this molecule? Or how could I like improve the solubility? And the words that they use to describe it, like really, it looks like they have very deep understanding of organic chemistry. Like they understand what's an electron withdrawing group. They have memorized all the groups, more than I could ever memorize. They know principles of like, catalyzing a chemical reaction, like what are good and bad decisions to make for specific reaction classes. But then when they stumble, it's like when they actually have to do the actual work of maybe drawing the molecule or like, doing the stoichiometry balancing. And in some ways, it's like what you said. It's not that surprising. LLMs have some handicaps, like they don't see words and letters like we do. They have these tokenizers that have kind of arbitrary boundaries. Some of the early like mistakes of, or I shouldn't say mistakes, but like some of the early language models, they were bad at arithmetic because like the number 342 was one token, whereas 343 was two tokens, 34 and 3, right? And so they work through these problems by like having very careful tokenizer construction for arithmetic, but nobody did the same thing for molecules. So like it can't just literally see the difference between maybe one molecule, like the carbons are all bundled together in a big group, and then the other molecule, the carbons are like two tokens. And so it's just a whole bunch of memorization has to do with mapping from these tokens to their actual meaning. So that's why one of the biggest improvements to make on a chemical reaction predictor transformer is the tokenizer. So in like chemical reaction prediction, this guy Philippe Schwaller was co-author on the ChemCro paper. He like wrote this one line of regex to tokenize molecules, and this like regex line has been tested, and it's like the best way to predict the outcome of a reaction. It's just the best tokenizer for a transformer. And that's been floating around the internet for a long time. And that isn't in like modern frontier LLMs. So it's not that surprising that they have trouble, just seeing molecules. But of course, all this stuff is just obviated once you put tools with LLMs, so they don't actually have to be looking at the molecules or predicting the outcomes.
Yeah. But I think, now that you mentioned arithmetic, right? Like that is maybe the most obvious example, right? Like, if you try to, multiply two, 10-digit numbers, right? From the top of my head, in one shot, like there's few people in the world who can actually do that, right? But, when you get a calculator, pretty much anybody with fingers, right, who has been exposed to basic math, can do it, with 100%, efficiency, right? So, I think it's the same idea to me, right? Like, the trick is not, well, why can't, the model do this, right? And we need to scale up, to 10 trillion parameters in order to be able to do arithmetic, right? Like the interesting question is, well, what are the calculators that we need to put in front of the model, right? So they can do all these things with 100% accuracy, same as a human can.
Yep. Yep.
So, one of the things that I mentioned was the AI co-scientist, and I know I had Vivek Natarajan, who's one of the main authors of that one, in the podcast. We were talking a little bit about it. Let me ask a spicy question. How is what you're doing, better or different from what Vivek and his team are doing at Google?
Yeah, I think what they're doing is that team is like trying to demonstrate what you can do with Gemini. And I think that's awesome. I've actually had a lot of success with Gemini. It's a very interesting model. I think it breaks some of the rules that we had about LLMs. Like Gemini can handle very long context and work with it. So you can have it run for very long conversations. I think that's where like co-scientist really shines, is that it can consider a whole bunch of information. And so it can reach these very long running trajectories that you don't get with other frontier models. Gemini also is very good like at document reading. Like Google has done, I don't know how they did this magic, but like somehow if you upload a PDF to GCS bucket, it can then be read by Gemini very easily. And so you can really like work with a lot of heterogeneous documents with Gemini. It's actually very impressive. But I would say that what they're doing is they're like, trying to build out like a demonstration. I mean, last I heard co-scientist was like, a set of scripts and not really like a website with a product in front of it. And I think they'll get there. But I think it was sort of a proof of principle. Now, I think they've de-risked it, and I hope that they go on to build something complete and build a model and maybe even train special versions with reinforcement learning or something. But I think what we're doing at FutureHouse is we're really going, I think, a little bit deeper on like building a specific set of tools for this workflow, right? Or building, like for example, in chemistry, we noticed that we couldn't really do inverse problems. Like molecular design is still not solved by frontier LLMs. There's just not tools to do it. So we trained our own reasoning models to handle that task. And so I think it's just, we have more resources, more, engineers devoted to the effort. But I think that is, I view co-scientists as like, I view it as like a research paper. Like they demonstrated like a paradigm and it works really well. And we've taken some of the ideas, like we did that pairwise comparison. They had this like ELO style tournament. We use that in our Robin paper, I think is a really cool idea. So I think it's, I view co-scientists right now as not really competing products, but more like like a project that demonstrated some really good research ideas, and I'm sure that team they do great work. So I'm sure they'll come up with the next iteration soon.
Yeah. I mean, if I would speculate, I think, that's a very interesting point, right? That you hit on, and very true. Sometimes Google would have, I can complain at Google because I spent 16 years there, right? As you know, right? So I'm allowed to do that. I think Google sometimes has problems kind of closing the loop, right? Like, there's, of course, lots of, really smart people having, really, amazing ideas, right? But sometimes you need to finish things, make it into a product and sell it and make money or whatever, right?
Yeah.
One of the things that the people are sometimes surprised, right? Just like now we talk about, ChatGPT this and OpenAI that or whatever, right? But like, before that, there was Lambda, that was T5, it was also like, I had been building this thing for, like half a decade, right? And it was only when the OpenAI folks, put this technology out there and then, put a Stripe checkout in front of it, then folks woke up and say, oh, this is interesting, right? Yeah. Like we can make money out of it, right? And then, it's a little bit of a scramble, right? For, 6 months or a year, right? To kind of catch up, right? Like, the quality of models, was not the same. And I think, now it's, basically on parity, right? But yeah, no, I think it's fair, right? Right now, if you think about an AI co-scientist or a system to use language models for science, I don't think there's any product out there. I don't think there's a good way to make money. I think the monetization models are still kind of, a little bit fussy, right? Maybe 2 years from now, somebody would go and say, oh yeah, we, did this and then, sold a new, molecule for, cancer, X, and then we made, $1 billion. And then somebody at Google would be like, okay, now we need to do this, right? And then the next year, we'll have a competing product that is, at the same level, right? But I think we're still kind of like, nobody has, closed that loop yet.
Yeah, I mean, I think if you want a real world example, a university is a place that's like a bunch of AI scientists, well, they're real scientists, but right, and universities they have a lot of trouble commercializing things and making money, right? Like I think that's what the patent system was invented to do. But you can just patent things and then assume you will make money from the ideas, right? And so, yeah, I think the monetization and the product of an AI scientist is a really tricky question. Like if you had an AI scientist, and you could put in money or compute and get out discoveries, it's actually not obvious how to make that into a viable business. I think co-scientist, I mean, I'm not Google, but if I were Google, I would make co-scientist like a demo of what you can do with Gemini. And I would I don't even know, maybe open source it or maybe make it like Notebook LM where it's just like part of a larger category of offerings. But turning a co-scientist into a product that you pay money to use is going to be hard. Maybe it's possible, but I think it would require a lot of careful thought and also like pricing too, right? One of the things about research is that in one hand, there's unlimited upside, right? Like if you make a molecule that cures cancer, yes, that's a $1 trillion opportunity. On the other hand, a lot of times people just ask things and they don't work out. And so I don't know how you price that correctly. But anyway, I think I'm excited that Google's participating. When we started at Future House a few years ago, the idea of building an AI scientist was like a ridiculous claim. And I think everyone thought, well, not everyone, but I think some people thought we were insane. And so now there's, multiple companies and multiple research papers about an AI scientist. I think it's great. And I'm looking forward to more people trying out this direction.
Yeah. I mean, of course, like there's always somebody that was going to say, yeah, that's crazy. That's never going to work, right? But at the same time, I think, there's a lot of people, down in the valley, right? Or, in a lot of other tech centers that, they're very good understanding, exponential growth, right? And how things move and stuff, right? And like the one thing that I think is pretty inarguable is that, the capability of these systems is increasing over time, right? So when you have something that is increasing over time, you have something that is fixed, which is, human intellectual capacity. At some point, those lines are going to cross. And at some point, one of the lines is going to go on top of the other, right? There's no question about it, right? We've seen it, right? And then when you have, technologies that are growing, exponentially, or compute capacity that is growing exponentially, at some point, one of these things is going to overcome the other, right? So, I mean, it's kind of like, it's not a comfortable discussion, I guess, for a lot of people. But at some point, some of these, tools or some of the systems are going to reach capacity beyond what humans can do, right? Like, they already can, memorize better than we can. There's no, question about it. There's no doubt, right? Like at some point they will be able to answer a customer call, better than a human can, right? It's not that complicated. You listen to somebody, understand the problem, look up some information, take some action, right? Is it really that revolutionary to think that they may be able to do, read papers and, formulate hypotheses and then design experiments and run those experiments and extract conclusions better than a human can? I mean, I don't know, right? Like doesn't seem that extraordinary to me, but of course, like I'm kind of part of this system, right? So I've drank the Kool-Aid, right?
Yeah, I mean, I think there's a lot of analogies in the past. When I was a new PhD student, we had like an orientation from a research librarian about how to look up research papers. And, they said, oh, there's this thing called Google Scholar, which is now available, but, you really don't want to rely on that because Google Scholar may not always be around. And so then they taught us how to go into the stacks of the library and find the paper. And they taught about how, things are organized like semantically or like across topics so that you can catch other journals while you're looking there. And if you flip to the journal, you might find an article is interesting. Really great advice. Obviously, like all the research librarian stacks, all the research libraries were closed in major universities to save money during the pandemic and earlier. And basically, you can't even go physically get journals at most universities. And Google Scholar is now the only way that people interface. I mean, of course, there are a few others, but like mainly Google Scholar is the only way you interface with accessing research or finding new research papers. So, like, I think that is definitely plausible for working with scientific literature going forward, is that there may be some AI scientist that just goes and does a precedent check. Has anybody ever done this before, right? Or like, what are the most compelling hypotheses? Or like, I have a hypothesis. Tell me, has anyone researched it, or what's the evidence for and against it? I definitely think that's on the near term future for AI for science. Whether we can automate the whole process, I don't know. This is something that I've been thinking about. Is that at the end of the day, a lot of research that's done is for a human audience, right? Like when something goes into Cell or Nature versus Cell Reports or, Nature Communications, the difference between those journals is usually like whether people find it exciting.
Mm-hmm.
Now, a model can maybe predict what humans think is exciting. So, maybe it will look like that. But I think that research for a lot of the time is like a human endeavor, as in humans think this is important or this is interesting or this is an important problem. So I think it'll be a long time before like scientific taste or like, the consensus on what is important science is automated away.
Yeah. Yeah. I mean, I think it's maybe not necessarily impossible to teach taste to language models, right? But that's going to be necessary. Yeah. In my mind, as you were speaking, I think it is most obvious in mathematics, right? Like in a lot of other fields, there's always some kind of, applied way of looking at things, right? Like, if, you're working in, drug discovery, right? Like you can make a purely utilitarian, kind of argument, or, I imagine like, most of chemistry, most of, any engineering aligned field or whatnot, right? But in mathematics, it's like, well, if I have a theorem about, prime numbers, right? Is that important or not? It may not be important. That may not be important for 100 years, right? But like, is it beautiful or not, right? And you kind of have to be a mathematician to understand when something is a beautiful theorem or not, right? Like, even I would imagine even most other scientists would have no idea like what makes a mathematical theorem pretty or not, right?
Yeah. I think it's funny to think about mathematics. I think mathematics is in some ways the most at risk of being automated because like theorem proving is a very direct and measurable outcome. And in other ways, it's the farthest away from being automated because like a lot of math is opinions. Like what is an interesting problem? What is a cool problem? It's a very human, I think, activity among mathematicians. Whereas if you go to like, say, chemical engineering, I'm a professor of chemical engineering, in my domain, a lot of the problems that we're solving are like real problems that need to be solved. And there's like a definite measurable impact on their solutions. So I could definitely see the decision making or the opinion being automated away of basically somebody's like, hey, we need to turn air into plastic, or we need to turn air into jet fuel. to solve carbon capture and, and elimination of fossil fuels. It's a very clear problem with a very clear solution. And so this sort of decision making or opinion, or like, is this a beautiful solution or not, doesn't really factor into it. So I think mathematics is a very interesting domain to think about. Like, can you automate it? And is it even meaningful to automate it completely?
Yeah. That's probably it. I mean, like within chemistry or chemical engineering, I imagine there's like a million problems that you could formulate around, any material that you're using, can you make it, stronger, or can you make it, better in property A, B, or C, right? Or can you make it cheaper to manufacture? Where like, literally you will never run out of problems.
It's funny you say that, because in some ways it's true, but in some ways it's not true, because organic chemistry, that field, I think, is like what do you want to call it? Like a post-engineering field. Organic chemistry had some grand challenges in the 90s and 80s, like making Taxol, the molecule, was a big natural product synthesis challenge. But then over time, like basically a lot of the work in organic chemistry, the frontier of research, moved away from molecules that are important for drug discovery into things that are just aesthetic. Like there are these crazy ring structures, or like how many groups can you pack onto the side? Hennumite chirality that's not centered in one part of the molecule. In organic chemistry, in some ways, the frontier of organic chemistry has almost become art, and as opposed to like solving a specific problem. And so I don't know if there's like this transition that happens in some fields of science where like they're trying to solve big, real challenges. And then at some point they solve them, and you have a bunch of people who are very smart and capable, and they just sort of decouple themselves from impact on the economy or GDP or something and start just doing crazy stuff. And I don't know, this is like, you can argue it goes full circle, like theorems of prime numbers, or I don't know, like complex mathematics was not impactful for 100 years after it was developed. Maybe that's going to be true for this organic chemistry, or maybe not, I don't know. So anyway, I think it's a fun exercise that there are some fields that have gone through this whole cycle of like solving grand challenges and then like left the grand challenges, and now are just sort of become something like mathematics.
Yeah. Interesting. Let's go a little bit. I actually, one of the questions that I had prepared was very related to that. Well, but maybe from a slightly different perspective. I think, from the point of view of somebody outside of the field, that are some like sexy problems, protein folding, right? Like AlphaFold and DeepMind and isomorphic. They've been doing a lot of work there, and the recent Nobel Prize was given for that and so on and so forth. So it's become, I guess, very popular, and it's a very sexy problem. I have to get into like, is it solved or not solved, right? Like, I think like anybody that goes, deeper into it would understand it. It's not a solved problem, right? And it's better progress, but like maybe what are some of the examples of things that are, I don't know, unsexy problems that should, receive more attention, or like maybe sexy problems that maybe, solve, some of this, technology?
Yeah, you're getting at something like, every time I go to a policy meeting or like a scientific philanthropy or program officers, like they always ask like, what's the next AlphaFold, right? That's what everybody wants to know, right? Because it's something where like now that it's over with, everyone's like, wow, I should have funded that, or like that was a great,
but a great show too, right?
Yeah. So I mean, I can list the problems. The challenge is that, can you make something that's so clean like protein folding, right? Where there's a clear competition every 2 years. You can describe the problem very neatly computationally, as like the input is a sequence of letters, the output is a bunch of XYZ coordinates. Wonderful problem. So I think one of them that's obviously the next step in protein science is function. Can you predict the function of a protein from the sequence, right? That's the next grand challenge. That is many sub-problems, like can you predict what chemical reaction a protein will catalyze? Can you predict where this protein will go in a cell? There's a lot of problems there that are I think, very exciting. And in some ways, protein structure prediction was a disappointment. Like we thought that the structure of a protein would unlock like function prediction, and would unlock knowing which chemical reaction it would catalyze, or unlock knowing where it would go. But in some ways, structure has become just another signal that is maybe even latent in the sequence, right? There's been some interesting work, I think, from ESM showing that you can predict properties without predicting structure, just from the sequence alone. And so in some ways, the protein structure is very important for some domains, but in other domains, the structure of the protein is actually just a latent variable that maybe doesn't even matter for predicting some properties of the protein. So other areas like that, in chemistry, we want to predict the toxicity of compounds. We want to predict the ADMET properties. This is something that is shared among all drug programs. is predicting these important compound properties, and it's something that is very data poor. There's the Open ADMET project, which is being funded in Silicon Valley. There's a group from Oakland, from San Francisco, from ECSF, working on measuring a whole bunch of these properties of compounds so that we can try to get a nice challenge data set like that was for protein folding. Other things, there's the virtual cell. I don't know what virtual cell is, but you can define it a lot of different ways. But I think a nice clean definition is can you predict like this gene expression or gene co-expression from cell perturbation? Basically, can you model a cell well enough that if I say I'm going to give it this compound, then can you predict how which genes turn on and off, or which proteins are expressed? That is, a big challenge is that if we can model that, then we can sort of do computational screening of compounds. So I think those are some of the challenges. None of them are going to be as neat as CASP, which was the competition for protein folding. None of them, I think, are as clean computationally to define, but certainly those are some of the next challenges in the space of biology and biochemistry.
Yeah. Jan Zuckerberg has been spending a lot of money on this virtual cells kind of ideas, and I think Recursion also had a big paper about it. As well.
Yeah. Recursion. I think. Virtual cell is an umbrella term that brought in like a lot of different areas. So Recursion has worked a lot in these like cell inpainting and cell perturbation models where you do high throughput imaging of cells and then look at transcriptomics data and then you put compounds in there to try to see if you can predict it. But then virtual cell includes first principles modeling and metabolic network modeling, systems biology. I think the virtual cell is like a nice umbrella term. I don't know if the solution to virtual cell at the end of the day will be some big model that does all of it, or if the virtual cell solution will be, some set of tools, like we have a set of tools for analyzing sequencing data, and there is not like one sequencing method, or there's not one sequencing technology. So I think it's in some ways like a policy tool or like a funding tool. Like you can say you're in virtual cell, but in other ways, I think it's a nice way to group together a bunch of ideas and a bunch of targets.
Okay.
Reaction yield prediction. Why is it so? Like coming from somebody who's not a chemist, okay? Somebody in computer science, you have your input and then you have your process and then you apply it, you get your output. You get the same output every time and you know how much output you're going to get, right? Like why is reaction yield prediction complicated, right? Why would my understanding is we don't even have good models for it, right?
Yeah. You bring up a really good question. Yeah. Okay. I mean, reaction yield is one of those things that you get a huge range of opinions on. Some people say reaction yield is a meaningless number because it just, like, everyone reports reaction yield of whatever, greater than 50%. Nobody's out there reporting reaction yield of 1%. I mean, maybe if it's like a long set of multi-step reactions, but reaction yield is just sort of like, you say, hey, what's the error bars on that's what like saying reaction yield is. But whether you can predict the error bars on data or whether you can predict reaction yield is just like not as important as predicting if the reaction will work or not. I also think you can see this reflected in a lot of people don't believe the reaction yield quality of data. So like if you look at there's a few sources of chemical reaction data that are out there. One of them is called ORD, or Organic Reaction Database. If you talk to people who curate that data set, they would say don't trust the reaction yields because in some people depositing them, they take it very seriously, and some people just throw in yields that are really kind of meaningless. The other thing is reaction yield is, it's probably not repeatable. Like if you have the same person or a different group run the reaction 3 different times, you will probably not get the same yield. So maybe there needs to be a change. Maybe yield needs to be replaced with like easy, medium, hard. I don't know. Or maybe like reaction yield should just not be modeled at all. I don't know. But I think it is like a very tempting number because a lot of people get excited about reaction yield because it's a nice floating point number in all of these chemical reactions and you can measure a nice RMSD with it. So I think it's a very tempting thing to model, but I don't know how important it is.
Okay. How about retrosynthesis? This is one of those things that I always thought, like this was interesting, right? Like you have, a lot of areas where, if you could only come up with a molecule with a specific shape or specific properties, right? But then you have this problem, like, why do you actually make that molecule in real life, right? In computer science, what happens once you have the software, the software, that's it. That's the end product, right? But yes, in chemistry, you kind of want to build things in the real world, right? Like, why isn't this a more important problem? Why haven't we seen I don't know, like AlphaGo for retrosynthesis, right? Like
like you would imagine that this is something that you definitely want to do, right?
Yeah, well, I will say that there is something like AlphaGo for retrosynthesis. Mark Waller and Marvin Segler wrote a paper in, I think, 2017 or something, and they did Monte Carlo research for retrosynthesis. Now, it was not exactly like AlphaGo, right? They didn't really have like a value network, and the other thing is you can't really predict retrosynthesis computation like you can Go. When people have applied some reinforcement learning methods, like in this paper, and then the molecular transformer paper by Philippe Schwaller, that was led to Alpha Lee, who then started Postera, which is a company that sells like retrosynthesis prediction services to pharma. And they're very successful. And then there's a couple like Reaxys and IBM and Chemical Abstract Services, CAS. They all sell reaction prediction models that do retrosynthesis. And they're quite good. But I think what happens is that retrosynthesis is one of those problems that's like not as clean as protein folding. Because like if I want to if I'm a chemist and I want to make something, I can go to retrosynthesis predictor and it'll tell me like, oh, take A, mix it with B, then mix it with C. And it's like, well, B actually is, not in my lab. I have to order it from this company, right? Mm. And so then what happens, the retrosynthesis becomes like a very personalized problem, is that I might go to the retrosynthesis predictor and I say, I want reagents that I can get into my lab within like a week. And I want you to make it as cheap as possible into the week timeline. Or somebody might say, only use what's in my lab. And it might take 5 steps instead of 1 step. Or somebody might say, I want it to be as cheap as possible. So make sure you get, you can order reagents that take 6 weeks out, right? And then there's also this decision making of like, okay, I can make this compound, but this compound relies on these like pendants or this core structure that I know my collaborator in Tennessee has some of this stuff available. So I should have him make it instead of me. Anyway, so retrosynthesis is like you can formulate it as a clean problem. And I would say it's been good work on that. But when it comes to like really using it in practice, you have to have all the complexities. I think that's why like Postera has been such a successful company, is that they like actually do a lot of the inventory management stuff, knowing how expensive everything is, knowing how long it will take to get there. But certainly there is like a version of retrosynthesis that is not solved. I would say like stereochemistry is not really solved in retrosynthesis. The models are they're okay at predicting the forward reaction, and so you run into this problem like you can propose a nice route, but then you don't predict the forward reactions all the way because like maybe there's some stereo effects there's some steric hindrance that you just can't capture with a transformer for predicting the forward reaction. So you have to go test it out in the lab. So I don't know. It's one of these problems that like you can, if you squint, it's almost neat like protein folding, but then if you really like see how things are going, it's more complicated. But I guess that was protein folding, right? Like we just defined that the problem was structure prediction for a 0 Kelvin cryo-EM structure, but that's not really what's happening in biology. I think you can reformulate retrosynthesis that way as well. But I think there's been enough good work in retrosynthesis and there's enough models being used that it's not quite viewed as much of a grand challenge. Whereas protein folding back in the day, there really wasn't a solution that could even give you anything plausible for most proteins.
Yeah, I mean, you could run a long-lived molecular dynamics simulation, right? And then birth a few million, I guess, like electricity, right?
Yeah, I think that was the biggest shock of protein folding, was like not that it was solved. I think everyone thought that DESRA's, D. E. Shaw Research, was going to solve it with their specialized, big computers. But what was surprising was that it was solved, and then within 2 weeks, people could run it on their own computers. So I think the biggest shock was that it wasn't a big computer that does it. It was like everyone with a GPU could do protein folding. And so for something like retrosynthesis, I think maybe the frontier is like that, if you can get it on everyone's desktop and they can do it easily and quickly, that's maybe exciting. But I think it's just not as clear as a challenge as protein folding. But anyway, that's a hard thing to ask, right? Like everyone wants to know what's the next protein folding challenge. I don't think we know yet.
Yeah. I mean, I think this was one of those things that I thought it was very interesting as well. But for me, coming from the mathematics, right? And I'll spend a lot of time doing AI, right? I thought, okay, well, obviously you have this, really complex multifactorial problem, right? But there's some kind of manifold, right? And then when you build your AI system, you're kind of collapsing into that manifold. And then, of course, you can compute it faster, right? And then it's like, well, it's the same reason why, you have, going to the next question, right? Like, you have the systems that can generate human faces, right? Like, how can you take, generating pixels is a very complex multifactorial problem, right? If you have 1,000 by 1,000 by, 16 million colors, you have a lot of dimensions over there, right? But, somehow these models are smart enough to go and generate a photo of a person, right? And of course, the reason for it is that the manifold of, human faces, is a much, much smaller dimension kind of a space than, the space of all possible, images, right? So I guess it would make sense that, there's a manifold of protein structures, right? Through, evolution or whatever, right? And that is a much smaller space than the space of all possible, kind of, conformations in 3D, right?
Yeah, I think you're getting on something very important. And I think that's like the difference between something like molecular dynamics versus a diffusion model, is that in molecular dynamics, you're tethered to this idea of you're actually simulating something physical. So you can't really move the protein fold. You can't have any self intersections. The protein has to fold in some kind of physical pathway. Whereas diffusion models, which is right now the best way to do protein structure generation and also generating images, you basically just drop physics completely, and it's just like a gas that basically forms into the right shape. It's a smooth surface. There's no like points of infinite energy that block your path. And then you end up in, like a nice smooth manifold where you can just move between all the faces or all the protein structures. It's a very nice formulation. And I think in some ways it's like, if you want to talk about dogma or like, impediments to scientific progress, people insisted that you had to use molecular dynamics. You had to do a physics-based method. And I think
physics, right? Like, how can you ignore the laws of physics, right?
Exactly. And I think David Baker was a big, I think David Baker deserves a lot of credit, not for the protein structure prediction that led to it, not like Rosetta Fold. Of course, Rosetta Fold is very good, but it was a big idea for him earlier in his career. Before 2010, when he was like, let's just go empirical, right? Let's just predict, from the protein structure database, get all the protein folds, and then just statistically model them and ignore physics. And I think that was a radical approach to build software and build a research group and a research career around ignoring physics.
Yeah. It was, I guess for the reference, people that may listen to it that may not have heard about it, but there was this famous kind of commentary, which was the unreasonable effectiveness of data, right? It was one of them. I think that was Peter Norvig. Was it Peter Norvig, the one that wrote that? I can't remember. I could look it up, but it doesn't matter, right? It was the unreasonable effectiveness of data, which says, if you have a lot of data, everything else doesn't matter, right? So you can ignore the physics as long as you have enough data, right? Like, you can ignore the physics. That was based on another older paper, which is a classic, right? Which is the unreasonable effectiveness of mathematics, right? Which talks about like, why does the world have a structure? Why don't we have magic, right? Why do things, seem to follow, laws, right? Anyway, it's like it's a fun, scientific, trivia.
Yeah. For me, I like the story of in the 90s when people were working on translation, and they had these NLP experts and natural language processing experts on a team. They had linguists on the team. And one guy remarked, every time they fire a linguist from their team, the translation improvement goes up. And this is goes back to the bitter lesson or something, is that a linguist likes to assign structure and assign rules and come up with grammars of how things should work. And then it turns out if you remove those rules and remove those inductive biases and you just rely on data, things just get better. And actually, we're seeing an echo of that right now, is that equivariant neural networks are very popular. And I think, AlphaFold 2 had this invariant point detection module, and it was a very influential thing because at the time, people like, I can't remember, it was Taco Cohen, I think, and Michael Bronstein, they've been really pushing this geometry design. I think it's great work. It's beautiful work. But if you look at AlphaFold,
intellectually, it makes a lot of sense, right? It's like, it has to be equivariant, right? Like the world is equivariant, right? Yeah.
But then when they did the ablation in AlphaFold 2, I think a lot of people didn't notice that if you delete the invariant point detention, the performance of AlphaFold 2 didn't really change. And so there's clues that equivariance may not be that important. And then there was the work from Zach Ulysses from FAIR, from Facebook, where they showed that basically in predicting structure of these homogeneous catalysis complexes, removing equivariance was also just you could make it back up with data. And so I think nowadays the the pendulum has shifted a little bit away from equivariance. I don't know if we're going to leave equivariance. Certainly there's some domains like where you just need to have equivariance, like translation equivariance and permutation equivariance just have to be in these protein structure predictions. But I think the rotation equivariance people are leaving behind. And so I think there's just lots of examples where just increasing the data is the most important activity you can do.
Yeah, I don't know if anybody really knows, right? Like, I think there was an interesting comment or a paper that came out. Somebody tried to predict planetary motion, I think. Yeah, it was like using a transformer to predict planetary motion, right? And then you go and ask the same model, well, can you predict the force fields that cause a planetary motion, right? And if you know a little bit of physics, well, the force field has to kind of, be a set of like different arrows, right? That kind of, move the planets around, right? And that's why the planet moves in a circle, right? Because the forces are kind of pushing it that way. But in this model, the motion was correct, but then the force field was all over the place. It was like arrows, like it made no sense whatsoever. And I was like, well, there's obviously no mental model behind it, right? Like, you could argue like the model is really not understanding, that the force field and the motion are connected, right? But like still, it predicted 100% correct or like, very, very correct force field, right? So at some point, I mean, I don't know. It's a little bit of a philosophical question, right? Like, do you need to build that poor model and have that deeper understanding of why things are happening, or can you make 100% perfect, predictions, right, without understanding any of it at all?
Yeah, this is great. This is a great debate. I think this is like one of those questions as well of it matters what the format of your data is. So in this like planetary example, maybe there was a different way to formulate the problem, like different coordinate system where it would just have to have like good force fields. And there's actually some really cool work from Miles Kramer, who's now I think professor at Oxford or maybe Cambridge, and he worked with DeepMind at an internship on predicting motion of planets. And what they did is they basically built a graph neural network that like was showing the message passing graph neural networks was sending messages between the bodies here to predict what the next frame would be in the simulation. And what they did is they then did symbolic regression on the messages. So they like compressed the messages into a closed form equation, and they were able to recover the law of gravity. And so they got out the right answer. But certainly if you just do a transformer where you have like an all-to-all attention mechanism, no sense of locality, and you're predicting it in XYZ coordinates, like I could see it has to learn some crazy variant, right? And I don't know, I guess this is maybe a counterexample to my previous point is that maybe there is, some structure is helpful, but too much structure is unhelpful. I don't know.
Yeah. I don't know if anybody knows, but honestly. Maybe last problem that I want to talk about, like what can we do with say synthetic biology? Like, this is one of those things that a few years ago it was all over the rage, and people were like, yeah, we'll be able to design all these amazing organisms and create enzymes that chew plastic and then generate oxygen or whatever, right? Like, why is that so hard? Like, it seems like it hasn't been a lot of progress in like decades.
Yeah, synthetic biology. Yeah. I guess it's one of these things where synthetic biology is a beautiful topic, right? Like when you think about molecular cloning and engineering organisms, there are all these rules that people learned about, like the grammar of these systems. It's amazing, super cool. Problem is that they don't really follow the rules. And this is the problem in a lot of biology is that, it sounds like you should be able to engineer organisms to express anything or to do anything. But then when it comes time to actually do the experiments, you find that you actually can't do a lot of the things that you should be able to do. They don't really follow the rules. So a lot of the time, the way that synthetic biology works is that you just do something that somebody else did and you change it just a little bit, or you work for a long time with trial and error. And so maybe this is the next, this is the next AlphaFold topic. But basically, synthetic biology is a really hard thing because it, at first principle, appears to be like a closed system with symbolic rules. But then when you go and start using it, you realize that it's really not that way. And actually, a lot of things are quite hard. And so there's this schism, I think, in synthetic biology, where there's some areas where you can really follow these rules to make proteins in specific bacteria. But then a lot of other things, the best way to make progress is with directed evolution, where you just try a whole bunch of ideas and with pooled screening and have to experiments. So then, if you want to ask why the impact hasn't been very high, I think Ginkgo Bioworks is like the flag holder for synthetic biology. And it turns out that just nobody has, I think, a lot of money to solve specific synthetic biology problems. People don't want to pay for specific synthetic biology problems. And that's that a lot of things are just really expensive in synthetic biology. Like, I think we probably do have enzymes that can cut through plastic. Like, I think that there's been papers on these things. But the scale up of like, how do you get these enzymes all over the place and actually get working on plastics is really expensive. It probably takes a lot of water, and also like they're probably not thermally stable, and there's a lot of really hard work that needs to be done. So anyway, I don't know. I guess synthetic biology is is still a dream. Like the actual engineering being easy to do and anyone can do it, I think is still a dream. But right now, there's some areas that are pretty like you can just go do really cool stuff like GFP expression, or using Puck19 to put things into cells is like pretty straightforward. But on the other hand, I think as soon as you try to do something novel, a lot of those rules break down.
Yeah. Like, what was it? Fluorescent zebrafish that you can put in your fish tank or whatever. Like people have done that kind of stuff. And, yeah, that's cool, right? But I guess, like, if you're worried about, I don't know, climate related stuff, right? You would imagine one of the first things that you may want to do, right, is like take all this, plastics, all this, trash in the ocean, and then just clean it up, right, with some, chemical system. And like, yeah, I mean, I don't know, it just doesn't seem like, or even better, right? Like, if you can somehow generate, natural gas, from other things that are less useful, for example, like you would imagine there's a lot of money doing that, right? And I don't know, haven't seen that much, use from that side yet.
Yeah. There's like this, I don't know, there's this problem in biology is like no free lunch sort of situation where you can engineer organisms. I've actually been in a project where we engineered organisms to basically take wastewater from a brewery and then take like photons from like hitting like nanoparticles. And then that's like your electron source. Then you have like the carbon source in the brewery and then use that to make fuels. And the problem is that it's not like there's no selective pressure to keep the organisms making fuels for you, right? Like they always mode collapse onto just reproducing in the most efficient way possible. And so you have to be like really clever in synthetic biology is that like a lot of times, if you make something that can make natural gas for you, there's a lot of natural selection pressure for it to not make natural gas for you because it's a completely orthogonal thing for it to be reproducing. So there's a lot of weird challenges in biology in that sense. And also like GFP is such a funny example because like sometimes people put GFP, like I was talking to somebody about a project where they have rhodopsin and they just put GFP on it. They always put GFP on it because GFP just expresses really well and goes to the right spot of a cell. And so there's a lot of things that just coincidentally fluoresce green out because they're like doing it because they just want GFP to make sure it gets expressed well and goes to the right spots. GFP is just like this really robust thing that just, I don't know, cells love to make it, people love to make it too. So the funny kind of thing where you have a lot of black magic in the field, and it's the opposite of, an engineering discipline. It's a lot of art.
Kind of running out of time. Let me ask one more question. Like you mentioned at the beginning, doing red teaming for GPT-4. For like people that might not know that, right? Like red teaming is like trying to figure out how to crack something, right? How to get this thing to do things that it shouldn't do, right? And now that we're talking about biology, right? Like how scared are you that somebody may, just take one of these, models, figure out how to make some, nasty, chemical compound, or how to introduce some mutation, and then, get some kind of, pandemic or disease out there, or like, some kind of like, toxic substance that they shouldn't, necessarily, have access to. Like, is that really a realistic concern, or is it, something where you say, well, like, it makes for great headlines, right? But like, it costs, millions of dollars to do it when you know how to do it, right? Like, nobody, from a, basement in, some, random country would be able to do it anyway.
Yeah, I think this is a good question. I think the short answer is that I'm not more concerned today because of AI models than I was, 5 years ago. I think a lot of it is that the information is already out there. Like you can download this genetic sequence for smallpox. You can download the chemical structure of cyclosarin or Novichx. Like all these things are available. So there's not really like an intellectual barrier to see the recipes. I think there is like a question of can they help you troubleshoot things in that like sort of tacit knowledge domain? Like if you go to make it and you need help, like the models are getting better at troubleshooting things. So certainly I think there is some risk introduced there. But these are some of the most difficult ways to like cause harm is making a virus. Nature has been making viruses for a very long time and does a really good job and makes the most effective viruses it can. But I think it's it's quite sci-fi that a human being could make, or an AI could make a very effective pandemic that can somehow with gain of function and some really complicated engineering really impact the world yet. Now, certainly it's something we want to pay attention to. Like, we don't want to be caught out. Like, there's been moments in AI research where the next generation model could do net new things that we couldn't really even imagine before. So I think it's something we should pay attention to. I think red teaming is so important. But I don't think there's any issues right now. And with that said, I think that for me, the biggest thing that keeps me up at night for AI progress is people's willingness to give up autonomy. So a lot of people like use LLMs to help make decisions, to write emails, to think about like how to do advertising, about like what business decisions to make, about what experiments to do next. And I do worry that like more of a risk is people giving up autonomy and how that can impact civilization long term. Is that if we do automate science, then LLMs are picking the topics and doing the science and doing the research. I think we're going to willingly give up control to these systems to a not such a good degree. That's what I worry about right now, not so much the super crazy weapons.
Yeah, I mean, I think in my mind, the biggest impact for the next few years, I completely agree, right, is going to be economic, right? Like, these things are going to be able to displace a lot of economically useful work. And then some people will just find that the jobs that they could do as human beings with certain intellectual capacities just does not exist anymore. Because any bookkeeping that you could do, ChatGPT can do the bookkeeping better, right? So if you are a person that is, maybe not necessarily a sophisticated tax accountant, right? But if you're a bookkeeper and you were doing bookkeeping, like maybe at some point there's no more bookkeeping jobs, right? The same way that, now there are no, horse, car transporting jobs, right? Because we have cars and that's it. And the horse car, transporting job, does not exist anymore. That will never exist anymore, right?
Yeah. I think these are the most pressing issues. I think people use biology and chemistry as like a punching bag in some ways, as like, oh, this is a real boogeyman. But yeah, I think cybersecurity, I think economic displacement and people ceding autonomy to these systems, those are, I think, the more immediate and bigger problems right now.
Oh, I forgot to mention, right? So the reason like this kind of, chemical weapons question came out is like, I had my OpenAI API key canceled because apparently I got an email saying, you're trying to develop mass casualty weapons, just like for asking, about like all this, viruses or whatever. And it seems like it was a common thing. I saw on LinkedIn, a whole bunch of people got their accounts canceled. So I guess I'm not the only one that is asking about like, like the actual mechanics of like, how COVID works, of how this protein, can get into the cell or whatever, right?
Yeah. I think this is one of those false positive, false negative trade-off things for them, So hopefully you got your account back though.
I did. It was actually very quick. I suspect that's why I'm saying, it probably affected a lot of people. And they said, let's just, reverse this whole change. It wasn't just like one or two people that were doing like, crazy questions or whatever. But yeah, I hope you didn't get yours canceled.
No. Luckily, no. We haven't got ours canceled yet.
Cool. Well, we're already out of time. But this was fantastic. Like, time really flew by. So, thank you so much. It was a super interesting chat. Maybe I'll be able to get another, a little bit of time, from you in the future. We could talk about, like some of the other, topics that we left in the air. But this is such a pleasure. So thank you so much.
Thanks for having me. It's great chatting. Bye-bye.